Hi, everybody. Welcome to the Data Show. I'm your host, Chris Greco. For the next 30 minutes, we're going to be talking about different parts of data, application, different statistical concepts, and how to apply those against maybe studies that you've seen or you've heard about and the things that come about as a result of that. So today what we're going to talk about is standard deviation. And it's funny because both of those words have different connotations when it comes to different things. But in statistics, it has to do with the distance, the deviation that exists from the mean. So you have the mean or the average, and that deviation is considered to be the standard deviation, SD for short. So basically, what is standard about it? And that's what we're going to be covering today with this program. Just to let you know, I'm also available on Roku TV and Pod TV. You can turn to Roku TV and Pod TV, put in the search Pod TV. The show is also there under the Data Show. I also like to put this on YouTube just in case people don't get Roku TV or they can't get Pod TV or whatever else. Then they can go ahead and take a look at this. Today's lesson, and it really is a lesson, an educational lesson on this statistical concept. So we're going to go through it. This is a relative. Everyone thinks about standard deviation and thinks about, oh, well, this is how to do it. This is not about the formula per se, although we'll show the formula. This has to do with why do it, number one, and two, what's in it for me as a person to be able to apply it to, let's say, data or any type of research study or anything else that mentions standard deviation. So those are the things we're going to be covering today. Sorry about that. It was a pollen thing. Okay. So let's talk about standard deviation. So first of all, some basic background. The standard deviation is based upon the mean or the average. The average is the arithmetic center of the data. And it's really interesting because when I would teach statistics and I would mention arithmetic center, people would sit there and say, is there another type of center? Yes, there's the median. The median is the physical center of the data with the data being sorted. So all these things are taken into consideration. The average is the arithmetic center of the data. And, it's the sum of the numbers over it's the value of the numbers, sum of the value of the numbers over the number of those numbers, right? The number of objects. And that's, it's really simple. We do it all the time. We take averages. Anybody that's been in school does it. That's those types of things. In a normal distribution, the mean is the center, literally trying to be the center of the data. That's where there is no abnormal distribution. I saw that written down one time. I thought, no, there's no abnormal. It's like normal, abnormal. It's normal and non-normal, right? So it's a normal distribution. And we'll talk about normal curves and all these things in a little bit. And then at any other part of the normal curve. So we'll talk about that. The standard deviation is the measure of distance from the mean, each of these measures being an even segment in what they call the normal curve. Again, we'll talk about that. We'll have illustrations, we'll have examples, all those things. However, the standard deviation is based on the mean, and the mean is not a robust measure of the center of data. In other words, it's influenced by both highs and lows. You have more highs, it's going to pop that mean up. You have more lows, it's going to pop the mean down. So the mean is the average, and because those averages, you could have 1, 2, 3, 5,000, and that high is going to pull that mean to the right. So it's going to pull that mean to the upper end, up. So that's what happens, and that's why it's very important that you have to understand standard deviation is based upon the mean. The mean is not robust. The mean, and because it's not robust, that's when it lends itself to some really interesting calculations. Okay, this is the formula. Now, the formula, when you take a look at it, you take a look at standard deviation. It has S here. Now, the problem is that we have S, so standard deviation. Standard deviation is equal to the sum of X minus the mean squared over N. Now, if it's a population, you're going to see this N here. If it's a sample, you're going to see an N minus 1. Now, what's the difference between those two? The difference is that n minus 1 is what they call a degree of freedom. And it's interesting to note that a lot of people, when I mention degrees of freedom, they kind of they close up. They don't understand what that means. But yet when I talk to them about Kevin Bacon and the 6 degrees to Kevin Bacon, they get that right away. And I said degrees of freedom are the same thing. The bottom line is this, is that you have six times to get an answer, but that answer is always Kevin Bacon. So it's, and they go, huh? I said, that's how simple it is. Basically, you have an answer. You're allowed to get that answer. It has to be Kevin Bacon at the end, but you have 6 degrees of freedom, 6 degrees of freedom to get there. You have 6 ways of getting there. Any way you do it, there's a lot of different ways you do it. But the bottom line is that sixth one or seventh, whatever it goes, you have to say Kevin Bacon. And if you take a look at it from that, then all of a sudden it starts to gel. It's like, okay. So if I have n minus 3, then I have 3 degrees of freedom. If I have n minus 1, I have 1 degree of freedom. That's it. That's it. So it basically helps to it basically allows for the sample to have a degree of freedom there, not like population. Also, the large n. And this would be a mu. It wouldn't be an x with a bar over top. And this would be a sigma, a small sigma. So rather than introducing all that, I'm just going to throw that out at you. And that basically is what's going on. Okay, normal curve. This is a normal curve. So let's talk about the different characteristics of a normal curve. And this is based on population. Why? Because there's your mu, which is your mean of your population, and sigma, small sigma, which is your standard deviation of a population. Don't worry about that at this point in time. This is a normal curve. Notice it's shaped like a bell. Now it could be a wide bell. It could be a narrow bell, but basically a bell. It's symmetrical, which means one side, if you turned it over, it would match this side. That's symmetrical. And both go out to a certain area. They never touch this line. The bell curve never touches this line. Gets close, gets really close, but it never touches it. That's the normal curve. So what does a standard deviation have to do with a normal curve, and what does it have to do with what does it indicate? The standard deviation, or SD, as you'll see it in these studies, indicates what the probability of something happening based on the distance from the mean, the deviation from the mean. In the next slide, the curve is segmented into basically 6 parts, 6 areas, right? This is standard, and that's basically what you have there. Each part's based on a mean plus the standard deviation as the first segment. The mean is the center. It's basically the center of the curve. Then as you start moving out, it's mean plus 1 standard deviation, mean plus 2 standard deviation, mean plus 3 standard deviation. On the other side, it would be mean minus 1 standard deviation, mean minus 2 standard deviation, mean minus 3 standard deviations. Okay, so that's it. So once you know standard deviation and mean, you can figure out your curve for that data. So what this does is it presents values that would have a lesser probability of existence as the curve goes left to right, right? As it goes left to right, you have the probability well, left to right and then right to left on the other side. So basically, from 0 this way, less and less and less probability, and then basically from this way to this way, less and less and less probability. So the curve goes out to either side. I know this is a quick explanation. I only have 30 minutes. Sorry. Here you have a normal curve. Now, Chris, you just talked about normal curve, but you talked about standard. Okay, we're going to talk about standard normal curve in a second here, but let's talk about normal curves, right? Normal curves. Normal curves, again, bell-shaped, whatever it is. You notice it has, there we go, 6 segments. 1, 2, 3, 1, 2, 3. The mean of the data, in this case population, is here. You have a mean plus 1 standard deviation, mean plus 2 standard deviations, mean plus 3 standard deviations. Same here, mean minus 1 standard deviation, mean minus 2 standard deviations, and mean minus 3 standard deviations on the left-hand side. So this is called a normal curve. Now, you sit back and you go, Chris, I'm still not, this is fine and dandy. Kind of getting it. I remember this brings back, horror and nightmares from my statistics realm, but basically you're going to get to what's going on. Yes, we're going to get there. Just hang with me just a little bit longer. So now you have the normal curve. Now, the standard normal curve. In this case, the mean is the mean, the standard deviation is the standard deviation. It's calculated. In this case, the mean is always 0 and the standard deviation is always 1. Well, that makes it easy, right? Because if the mean is always 0, then mean plus 1 standard deviation is going to be 0 plus 1 or 1. Mean plus 2 standard deviation is going to be 0 plus 2 or 2, because 2 times 1 is 2. So there's your 2. 3 is here. Same here. Mean minus 1 standard deviation would be -1. Mean minus 2 standard deviation is going to be -2. So now you have these areas, and what they translate to what they call standard z-score units. Standard z-score units based on a normal distribution. And thank you very much to whoever did this. I appreciate that. This is important. And we'll come to, so what we're doing is we're going to try to take this right here, right? We're going to take this and we're going to translate it into this. Everything can be translated, all data, as long as it has the mean and standard deviation, can be translated to standard z-scores. Well, what difference does that make? So what is a standard and standard deviation? The standard is called what they call a z-score. By converting any data into the curve, normal curve with a standard deviation, the standard normal curve, the analyst can then transition to a z-score to compare two disparate data values. And people sit there and go, really? I said, yeah. An example would be taking the heights of men or women ages 40 to 49, comparing them to the heights of men or women 60 to 69 using the standard deviation and the z-score. So the z-score is calculated to take the percentage of that height minus the mean and divide that by the standard deviation. Yeah, I know it sounds, what the heck? But let's talk about this. So we're going to do an example in Excel. So I got this table, and this table shows a percentage of the number of inches that a number of feet in inches, but I translated it to inches here, of men and women, males, females of different ages, right? So what I did was I got this, by the way, from this right here. So this is where I got the table from, right here. You can also get the same table. But the thing is, it's cumulative. See how it rises like that? So what I had to do first thing was I take the 40 to 49 years here. And what I did was I took this. Well, these are all zeros. 1, 2, 3, 4, 5. They're just so small that I basically made them zeros. So that's why they're all zeros here. But this 1.9 and 1.9, where did I get that from? I got that from this here, 3.8 minus 1.9. Then 5.6 minus 3.8, then 9.8 minus 5.6. Because I didn't want cumulative. I wanted to show the different percentages for each one of the inches of height. How do I know I'm right? Well, I can do this. I can say equal sum of this. Now, this should turn out to be 100 because that makes it 100%. So let me see if I did it. 99.9, close enough. This is a rounding thing, okay? 99.9, there's a lot of rounding here. That may be hundredths, thousands, or even 10,000ths of decimal point in here with these percentages. So close enough. I'm in good shape. As long as it's equal to somewhere like 99.9, 100, then all these will add up to exactly what I want them. Now, here's what I have. Now I sit back and I go, okay, well, I want 60 to 69. So I take the 60 to 69, same thing. I had a cumulative. Instead, I took 1 minus the one before it, and I was able to get the actual percentages for each of those heights. I hate dealing in percentages, and here's the reason why. Percentage is actually a derivative of the raw number. By dealing in percentages, basically, and the way I explain to my students is you have the problem is that you don't have raw numbers. So it's kind of like taking remember Kool-Aid, where you had a powder and you had to put, or even Gatorade, whatever it is, and you pour the powder in the water. Well, if you keep adding more water and more water and more water, pretty soon all you have is like green water or red water, orange water, whatever the flavor is. And that's the same thing whenever you have a derivative of a percentage. Most of the time it turns out okay, but raw numbers are really what you want to work with when you work with data, because percentages is basically a probability of something happening. So, in other words, there's a 1.9% chance that a man age 40 to 49 will be um, 63 inches, right? Whereas there's a 10.9% chance that they will be 68 inches, and 10.1 they'll be 69 inches, and 14% that they will be 70 inches. So, all these things you take a look at and you go, well, that's really interesting, Chris, but how does this relate to standard deviation? Well, first of all, I took the standard deviation and the mean from each of these, and it was relatively easy. Matter of fact, you can see it right here, STDEV. Now, you took the sample because it's a sample, right? I could have done population. That's fine. Either one. In fact, I can change this from S to P and do it that way. So that, and then this way, if I do it under population, I have that N aspect there. 5.06. See, you're not going to see much of it. This is 5.29. Now let's see what P shows. 5.16. 5.94. P shows what? 5.79. So there's a slight difference there. So this mean and standard deviation is really important. And you can, again, get it there. And here's your mean. It's average. It's really funny. A lot of people think, I'm going to put equal mean in Excel. Well, guess what? You put equal mean, you don't get anything. It's equal average, because, and I don't know why, they never really made that transition to mean, but the average is what you use here. So anyways, this is what you have. And I even took the difference between males 40 to 49, 60 to 69, between and it's interesting. It really is interesting, because at 61 inches you have 0 at 40 to 49. Now you have zero point 0.4. So the difference is you actually had an increase of individuals, a percentage increase of individuals that are 61 inches, yet none here. Slight increase here at 63, slight increase here at 0.2, 1.6, 2.7. This is, again, these are older individuals, but you actually have more of a percentage. Then all of a sudden 67 happens and you get a negative. But 68 and 69 happens and you have an increase between 40, 49, 60 to 69. So I mean, and then you have not too many. Once you get to 70, then everything, minus 5% here, minus 0.2, minus 0.2. So once you get 70, 71, 70, at 73, you have like 1% more, between 40, 49, 60, 69. So I thought that was interesting. Female, and I did females too. Now, what does all this mean? Well, basically, what I'm doing is I'm going to try to do a standard deviation based on the z-score. Here's your z-score here. Now, basically, what I have is I have mean, standard deviation, and what I did was I took the x, it's called a random variable, but basically a random variable is that variable which you pick from the data. That's why it's called random. It's not really like a random, like you get it out of a hat. You can, but basically a random variable is that variable which you are focusing on to try to standardize into the z-score. So that's, in this case, I put about 4%. So at 4% for female 60 to 69, I have a z-score of negative 0.17282. But let's do something positive first, just so we can have it. There we go. We'll get to go do here. So we have 9. So we're going to compare 9 to 9 here. And here you have that at 9, you have a z-score of 0.69 here, and you have a z-score of 0.82 here. Well, what does that mean? What exactly does that mean? Well, that means that if you're taking a look at this, that there are approximately about 32% more, 32% people of 32% of the people, 9%, wherever that may be, is going to be higher than than um, than that percentage. So in other words, there's more than 9%, 32% of the time. Here, there's more than 9% at 28% of the time. So, in other words, of all these percentages, when you take a look at this percentage, you're taking a look at this 9, and 9 or greater, basically, you have about a 32%, 30, about a 31% chance, 31% chance of one of these figures being more than 9%. Same thing here. It's going to be 18% is going to be more than 9%. So that you're covering the percentage. It's not so much the height, it's the percentage. So that's where a lot of things kind of are weird about this whole thing. But that's basically what you're talking about. And the mean here is going to be 5. That's the mean of the percentages. The mean of the percentages. So basically, if you have a percentage of 14.2, right, which is going to be pretty high here, you're going to have 1.55. Now, let's take a look at this for a second. Your z-score is 1.55. Your z-score here is 1.79. Now, let's not worry about probability and everything. I probably confused you with that. But let's move into the actual scores. 1.55 versus 1.79. And now let's go back to where we were here. So we're going to go back to this. And we had 1.55, 1.55, and 1.79. So this is where we have this. Normal curve with standard deviation. Here it is. There it is. X, which is random variable, minus the population mean over the population standard deviation. We just did that. That's how we got the z-score. So remember, one was 1.55. So 1.55 is about here. Okay. And 1.79 is about here. So basically what you're doing is you're taking a look at this entire area, and you see that 1.79 is closer to 2 than 1.55. So that means that that percentage, that 14%, occurs at that 1.79 level here, but it only occurs at 1.55 level here. There's more of the curve underneath that 1.79 than there is at the 1.55. That means there are more. There's there is more from all the way here to all the way here. Lot of data, right? So right here, there's 95% of the data here, 99.9% of the data here, 68% of the data here. So basically what you're doing is you're covering a lot of data when you're covering 1.79. You're not covering as much data. So there's not as many within that 14% as there is here for the 40 to 49. So that's what that means. Basically, you can compare that, and that helps you be able to understand exactly what's going on with the data. So 1.55, right? So that means less women are at that 14% than women 40 to 49. So that's what happens when you compare it. And interestingly enough, if you compare here at the male at 14%, there's at 1.88. So they're more than the women at 1.79. There's more curve at the 1.88 than there is at 1.79. So yeah, I mean, so that's basically what happens. And also I did this so that it's, these are very easily done. And I show this in another YouTube video. So it's not so much percentage that's shown here under the z-score. It's the amount of curve that you have within from all the way to the left-hand side to that z-score. That's the important part. Then the amount of curve that's in there, and that's how you can take it and compare, different bits of data rather than just trying to compare them. You'd compare them using the standard normal curve, and that'll help you. So why all this being done? Well, there's a study that was done that was basically looking for Flynn effects in a recent online U.S. adult sample, examining shifts within a SAPAS project, but basically it's IQ. And the IQ thing, when they talk about it, and I'm just going to roll down here to the actual data. It's a good study, folks. But here's what we have. This is when they talk about slope, they talk about standard deviation. So take a look at this standard deviation here. Look, I want you to take a look and see look how small this is. Look how small that standard deviation is. I mean, very, very small. Very, very, very small. They compare, so in other words, it's decreasing. And they really, really hammer on the fact that the standardized testing, the IQ aspects is decreasing in these different ages. In fact, all the ages are decreasing. But look at the amount it's decreasing: 0.012, 0.015, 0.024. And if you keep on going down here, you can see some of these graphs. And these graphs really, I mean, they're good. Don't get me wrong, study is good. The study it's well done. It had a lot of limitations in there. You have to read the limitations. We'll go through maybe a couple of them here. But this is when you go to the trends, this is where, and I talked about this in the last show about regression analysis, right? If you do straight line regression, basically everything looks bad. Oh my gosh. But look at what we're talking about. Between 1 and -1 in standard deviation. We just talked about this. 1 and -1 in standard deviations. 1 and 0, and then 0 and -1. So basically 2 standard deviations is what we're talking about here. So, and these are small: 2.4, 0.6, 0.8. So there's small differences, folks. They're small within that area. And I think that I think what happens is that we tend to take it more seriously, when we talk about these negative aspects, when in fact, realizing that this is a good visualization, you have to be careful about those visualizations. They will fool you. And those are the things that go on there. So it's that type of area that you have to understand. And that's why this normal curve of the standard deviation is very important. So how's it applied? We talked about this, the IQ scores. The SD will be shown on the normal curve in the previous slide, and I think you'll agree that it is very small. It is very small, right? 0.2, 0.4, you're talking between 1 and -1 standard deviations. That's it. I mean, not 3, it's just between these two areas. So it's very small. Visualizations and other illustrations, they can prove to be very influential in persuasion, but they can also be misleading. Not that the study tried to do that. They presented the data, they presented everything that they had there, but I think that that's pretty important to understand what the difference is and why those differences exist. And in all fairness, and really, it's, in all transparency, the data, it does talk about limitations. And the limitations were really, I mean, the measures, they did different measures, demographics, regression analyses using estimated birth year. I mean, a lot of the things they did here were really, really good. And they talk about this stuff, and then the different aspects. But they did also talk about limitations, and I will give you the actual I'll give you well, that ain't gonna work. So basically that I wanted to make sure and find these limitations because I think it's really important to understand. And here it is, limitations. So limitations here were really, I mean, they really talk about them very well. I mean, they talk about the fact that they were mostly female. 68% were females, in this whole thing. So it's in particular demographics of these subsamples are sometimes under or over sampled. They talk about they talk about different aspects: 60 years old, the age, I mean, and they did talk about in here the fact that they were mostly females. So I mean, that's just the quick and dirty on standard deviation. So hopefully, I'm probably going to hit this again on another show just to make sure that everybody understands what's going on. Sorry to make it so quick. It's only a 30-minute show. But standard deviation, a little bit about it, a little bit of how it's applied, and a study to kind of put that into effect there. So just remember that standard deviation is just one tool, one statistical tool that you can use. It is extremely important, and I will go into it in more detail in a future show. Whew. So for the data show, this is Chris Greco signing off until next time, when we will discuss data, we'll discuss statistical tools, statistical applications, and understand exactly what it is that we need to check with relation to data. Have a good day, folks.